Introduction. This module is the third in a series on the basics of mechanical ventilation in ventilators. You should first complete the two modules. Lung ventilation, natural and mechanical. Ventilator system concept. Otherwise, some contents in this module may be difficult to understand. In this module, we will learn about 5 essential variables and 8 mechanical breath types. The essential variables serve as the foundation of mechanical breaths, while mechanical breaths are the foundation of ventilation modes. The essential variables are directly related to the major ventilator control parameters. They belong to the core of intermittent positive pressure ventilation, IPPV, regardless of ventilator brands and models. After completion of this module, you should be able to answer the following questions correctly. What breath cycle time, inspiratory time and expiratory time are? What triggering, cycling, controlling, targeting and baseline pressure, and their mechanisms are? What a mechanical breath is? What the properties of 8 mechanical breath types are? It will take you 30 minutes to complete. Mechanical breath timing. Mechanical ventilation can be viewed as a process composed of a series of mechanical breaths. A mechanical breath is defined as any breath realized through a ventilator system. There are 8 types of mechanical breath. They will be explained later in details. To carry out mechanical ventilation, a ventilator must receive the commands from its operator on when inspiration should start and stop, when expiration should start and stop, how the delivery of inspiratory gas should be controlled, how big the mechanical breath should be, how high the baseline pressure should be. Every mechanical breath takes a certain length of time to complete. The duration is breath cycle time, BCT, or total cycle time, TCT. BCT always contains 2 portions, inspiratory time TI and expiratory time TE. Conventionally, TI comes first. During inspiration, a ventilator delivers the gas into a ventilator system, resulting in the airway pressure to rise and the lungs are inflated. During expiration, the ventilator stops gas delivery and allows the gas exit the ventilator system, resulting in the airway pressure to drop and the lungs are deflated. BCT, TI and TE are specified with 2 time events, triggering and cycling. Both are the essential variables. Triggering. Triggering refers to the time point when inspiration starts. Cycling refers to the time point when inspiration ends. So, TI is the duration from a triggering point to the following cycling point. TE is the duration from a cycling point to the following triggering point. BCT is the duration from a triggering point to the next triggering point. Triggering can be realized with different mechanisms. The common ones are time triggering, pressure triggering, flow triggering. Both pressure and flow triggering are regarded as patient triggering. Time triggering is also known as machine triggering or ventilator triggering, and is based on BCT, which is defined with a set rate. Once the rate is set, the ventilator automatically converts the rate to BCT with a simple equation. Breath cycle time in second equals 60 divided by the set rate in breaths per minute. In other words, every set rate has a corresponding BCT. For instance, if you set the rate to 10 breaths per minute, the resultant BCT is 6 seconds. If you set the rate to 20 breaths per minute, the resultant BCT is 3 seconds. The scale shows the commonly used rates and the corresponding BCTs. A BCT is the interval between any two consecutive triggering points. Whenever the defined BCT is over, the ventilator delivers inspiratory gas. Currently, all ventilation modes in Hamilton medical ventilators allow the patient to trigger unless patient trigger is deliberately disabled. If so, an active patient can dominate the actual rate, which is often higher than the set rate. If the patient is passive, however, the actual rate and the set rate are equal. Therefore, the set rate usually serves as the minimum or backup rate. Pressure triggering. Pressure triggering is a form of patient triggering. It relies on circuit or airway pressure monitoring. One way to understand pressure triggering may be that you suck an empty wine bottle. Your effort generates a negative pressure inside the bottle but little gas flow. The stronger you suck, the more negative the pressure is. If pressure trigger is activated, the breathing circuit serves as the wine bottle. The patient's inspiratory efforts cause the airway pressure to drop from the current baseline. If the pressure drop reaches a set virtual threshold, the ventilator is triggered and starts delivery of inspiratory gas. To utilize pressure triggering, you must activate pressure triggering and set pressure trigger sensitivity. The sensitivity is a negative value in centimeters of water, such as -0.5, -2 or -5 centimeters of water. The value represents a virtual pressure threshold below the current PEEP. For instance, if the set PEEP is 5 centimeters of water, and the trigger sensitivity is set at -2 centimeters of water, the ventilator is triggered if the actual airway pressure drops to or below 3 centimeters of water. The smaller the absolute value of the sensitivity, the more sensitive the triggering, and vice versa. So, pressure trigger of -0.5 centimeters of water is more sensitive than that of -2.0 centimeters of water. Flow triggering. Flow triggering is another form of patient triggering. It relies on circuit or airway flow monitoring. To make understanding easier, let us first specify 3 flow types. Flow A, the gas flow measured at the inspiratory limb of the circuit. Flow B, the gas flow measured at the expiratory limb of the circuit. Airway flow, the gas flow measured at the airway. It can be either inspiratory or expiratory. Further, let us divide expiratory time into early expiration and later expiration. Early expiration. At early expiration, the ventilator closes its inspiratory valve and fully opens its expiratory valve for a maximum expiratory flow. The high circuit pressure drives the gas out, and the airway pressure drops sharply. Both the flow B and the expiratory airway flow rise quickly to maximum and then decrease gradually as the circuit pressure drops. Late expiration. At late expiration, the ventilator tries to rebuild and maintain the set baseline pressure by A, reducing the expiratory valve opening for a high resistance against the expiratory flow, and B, opening slightly the inspiratory valve for a constant base flow, which is crucial for flow triggering. If the patient does not inhale, both the flow A and flow B are equal to the base flow, and the airway flow is 0. If the patient inhales, a part of the base flow goes to the patient, resulting in an inspiratory airway flow and a decreased flow B. If the detected inspiratory airway flow or the difference between flow A and B reaches a defined threshold, the ventilator is triggered. To use flow triggering, you must activate flow triggering and then set flow trigger sensitivity. The sensitivity is expressed in liters per minute, such as 0.5, 1, 2 or 5 liters per minute. The smaller the set value, the more sensitive the flow trigger is, and vice versa. For a ventilated patient, flow trigger is generally easier than pressure trigger under the same conditions of use. Abnormal patient triggering. Unlike time triggering, the patient triggering, both pressure and flow, can fail in two forms. The first form is that a ventilated patient has inspiratory effort, but the ventilator does not respond. The common causes are either the patient's effort is too weak, or the patient triggering setting is not enough sensitive, or both. The second form is auto-triggering, which means that the ventilator is triggered when the patient does not inhale. Typically, auto-triggering appears as a series of quick and rhythmic mechanical breaths. Auto-triggering occurs when the ventilator is triggered by pneumatic artifacts, but not by the expected patient's inspiratory effort. The artifacts often result from gas leak, condensed water in the circuit, or even cardiac oscillation. Another possible cause of auto-triggering is that pressure or flow trigger is set to an overly sensitive level. The best remedy for auto-triggering is to remove the root cause. If this is not possible, you may carefully decrease the patient trigger sensitivity until auto-triggering disappears. Bear in mind that this makes triggering harder for the patient. Cycling. Cycling refers to the end of inspiration. It determines the length of inspiration. BCT is the sum of TI and TE. If BCT is given, an increase in TI causes a corresponding decrease in TE, and vice versa. Time cycling and flow cycling are commonly used cycling mechanisms. Time cycling. With time cycling, you can define TI in several ways, including TI, I/E ratio and peak flow. Time cycling by setting TI. In this case, an operator directly sets TI in seconds. The ventilator switches from inspiration to expiration when the set TI is over. This method applies to both volume and pressure breaths. Time cycling by setting I/E ratio. Every breath cycle time or BCT has two portions, TI and TE. The ratio between TI and TE is I/E ratio. The number on the left of colon represents the TI portion and the number on the right the TE portion. Assume that we set the rate to 10 breaths per minute for a BCT of 6 seconds. If the set I/E ratio to 1 to 2, the resulting TI is 2 seconds, and TE 4 seconds, respectively. The advantages of I/E ratio are, A. A change in either I/E ratio or the set rate causes corresponding changes in both TI and TE, and B. The relation between TI and TE is clearly shown. The disadvantage is that you do not get TI and TE in second without mental calculation. Note, in an active patient, the actual breath cycle time, TI and TE may differ from the expected values. The I/E ratio method applies to both volume and pressure breaths. Time cycling by setting peak flow. It is a bit confusing. How can TI be defined by setting peak flow? Peak flow refers to peak inspiratory flow. This method applies only to volume breaths with a square flow pattern, meaning that a ventilator delivers the gas at a constant flow rate during inspiration. Under this condition, VT is the product of TI and peak flow. Therefore, TI increases when you increase the set tidal volume or decrease the set peak flow, or both. TI decreases when you do the opposite. Flow cycling. Flow cycling is another way to terminate inspiration based on the change in inspiratory flow. It is designed for active patients and is the key property of support breaths that we will discuss later. In a pressure breath, the inspiratory flow is uncontrolled. Typically, the inspiratory flow rises quickly to the peak at beginning and then drops gradually back to zero. Flow cycling works with the descending part of the inspiratory flow. the peak inspiratory flow is taken as 100% regardless of its absolute value. A ventilator switches from inspiration to expiration if the inspiratory flow drops to a preset level in percent. If the flow cycling is adjustable in your ventilator, you can find the control of flow cycling. In all Hamilton medical ventilators, this control is labeled as expiratory trigger sensitivity, ETS. You can set it anywhere between 5% and 80%. This control is unavailable if flow cycling is fixed at factory. Flow cycling enables you to influence the TI of spontaneous breaths. The lower the set percent, the longer the TI is, and vice versa. Flow cycling is very useful to improve patient ventilator synchrony. Flow cycling can fail if the system has a massive leak and the ETS is set very low, because the inspiratory flow cannot fall to the set cycling level. The consequence is endless inspiration. This is clinically unacceptable. To avoid this possible incidence, a ventilator has a backup time cycling, which may be adjustable. If so, you can find a control for that. In Hamilton medical ventilators, this control is called maximal inspiratory time or TI maximum. Controlling. The third essential variable is controlling. Controlling is defined as the mechanisms on how a ventilator controls gas delivery during inspiration. There are only two primary controlling types: volume controlling and pressure controlling. At any given time, a ventilator can only control either the volume or the pressure, but not both. In addition, there are two extended controlling mechanisms. Pressure controlling has a variant called adaptive controlling. Some ventilators have hybrid controlling. We will explain them one by one. Volume controlling or flow controlling. A better term for volume controlling is flow controlling, because during inspiration a ventilator actually controls the flow of inspiratory gas delivered into the circuit. At the end of inspiration, the set tidal volume is delivered. Volume controlling is shaped with three primary controls: VT, TI and peak flow. Typically, we set either VT and TI or VT and peak flow. The ventilator calculates the third one automatically. Volume controlling may have a secondary control: inspiratory flow pattern. Square flow pattern is the most common one. Some ventilator provides only square flow pattern for volume breaths. However, some other ventilators provide more flow patterns. For example, Hamilton G5, S1 and C6 ventilators provide square, descending, and sine flow patterns. The major perceived advantage of volume controlling is stable tidal volume as well as minute volume, with which we may feel comfortable. However, volume controlling has four inherent disadvantages. With volume controlling, a ventilator dictates all important aspects of inspiratory gas delivery. This is hardly acceptable if the patient is active. This explains why patient ventilator asynchrony often occurs in volume modes. With volume controlling, the tidal volume that a ventilated patient receives is always less than that a ventilator delivers into the circuit. This is due to gas compression in an elastic breathing circuit. The tidal volume difference is invisible volume loss. For instance, if the set tidal volume is 500 milliliters, the patient may only get 450 milliliters. This invisible volume loss needs to be corrected by circuit compliance compensation. With volume controlling, leak compensation is impossible because a ventilator delivers exactly the set volume into the circuit. With volume controlling, the peak pressure is variable, dependent on the set VT, peak flow, the patient's respiratory resistance and compliance, and breathing efforts. A constantly high peak pressure can damage the lungs. Due to these disadvantages, Volume controlling has given place slowly but steadily to pressure controlling. Pressure controlling. With pressure controlling, a ventilator first draws a target airway pressure profile according to the settings of TI and inspiratory pressure. During inspiration, the ventilator dynamically adjusts the inspiratory gas flow to minimize the gap between the actual airway pressure and the target pressure profile. This means, the ventilator increases the inspiratory flow if the monitored pressure is much below the target pressure. It decreases the inspiratory flow if the monitored pressure is a bit below the target pressure. It stops the inspiratory flow if the monitored pressure matches the target pressure. Pressure controlling is shaped with two primary controls, TI and inspiratory pressure. Inspiratory pressure refers to the intended positive pressure applied above PEEP. It drives gas to move into the lungs. In Hamilton medical ventilators, inspiratory pressure is labeled either as pressure control for mandatory breaths, or as pressure support for spontaneous breath. Pressure controlling may have a secondary control, pressure ramp, P ramp, or rise time. It is defined as the time required for airway pressure to rise to a target pressure at the beginning of inspiration. A short P ramp means a fast circuit pressurization, and vice versa. If volume controlling is compared to a dictator, pressure controlling is somewhat illiberal because VT and inspiratory flow can vary per the patient's demand. Because of this important property, patient ventilator asynchrony occurs much less frequently. When the system has a leak, causing circuit pressure to drop, the ventilator immediately responds with increase in the inspiratory flow. This is how leak compensation works. With pressure controlling, a ventilator can effectively compensate a moderate leak. With pressure controlling, the tidal volume is variable, dependent on the set inspiratory pressure, the patient's respiratory resistance and compliance, and the patient's breathing efforts. Under unfavorable conditions, the resultant tidal volume can be too large or too small. It is important to set tidal volume alarms properly to safeguard the patient. Adaptive controlling. Adaptive controlling represents the outcome of the efforts to exploit the advantages and to minimize the disadvantages of both volume and pressure controlling. Adaptive controlling is a variant of pressure controlling. With pressure controlling, the inspiratory pressure is set, the peak pressure stays stable, and the resultant VT may vary. With adaptive controlling, the inspiratory pressure is automatically regulated breath by breath to match the monitoring VT to the target VT set by the operator. In detail, the ventilator does the following. Increases inspiratory pressure if the monitored VT is below the target. Decreases inspiratory pressure if the monitored VT is above the target. Keeps inspiratory pressure unchanged if the both tidal volume are equal. Adaptive controlling may be misperceived as volume controlling because tidal volume can be set in both cases. Other than that, they have nothing in common. Here the waveforms of volume, pressure and adaptive breaths exhibit the similarities and differences. The major advantages of adaptive controlling are: A. The actual VT can be rather stable, especially in passive patients, and B. It keeps most advantages of pressure controlling. For optimal performance, adaptive controlling has a hard, yet rarely mentioned requirement for the operator. The target volume must be always adapted to the patient's current ventilatory demand, which may change over time. An unfavorable scenario is that the target volume is set lower than the current demand. The patient has to breathe harder to satisfy the demand. As the monitored VT exceeds the set target, the ventilator reduces the inspiratory pressure. At the end, the patient does all work of breathing, and the ventilator does little. Hybrid controlling. Hybrid controlling is defined as application of both pressure controlling and volume controlling within the same mechanical breath. In Chet-Burn's taxonomy of mechanical ventilation, hybrid controlling is named as dual control. Typical examples include volume assured pressure support, VAPS, mode of Bird 8400 STI ventilator and volume control mode of Mackay ventilators. We will not go deeper with hybrid controlling because it is complicated to understand and has not been popularized thus far. Targeting. Targeting is the fourth essential variable to define the size of a mechanical breath. Targeting is also known as limiting with the same meaning. Targeting is always paired with the controlling type. The target parameter is tidal volume with volume controlling, inspiratory pressure with pressure controlling, and target tidal volume with adaptive controlling. When the set targeting is reached, a ventilator stops delivering further gas into the circuit. Reaching the target, however, does not necessarily mean immediate cycling from inspiration to expiration. PEEP, the baseline pressure. PEEP stands for positive end expiratory pressure and is the baseline pressure above which inspiratory pressure is applied intermittently. This is the fifth and the last essential variable. PEEP is expressed in centimeters of water, and counts from zero or atmospheric pressure. PEEP is adjustable in all ventilators. PEEP is generated by interaction between the expiratory gas flow and the resistance imposed by the expiratory valve of the ventilator. PEEP alone is therapeutic as it can increase functional residual capacity, FRC, improve alveolar gas exchange, keep the lung units open, and even improve lung compliance. A moderate level of PEEP, 3 to 5 centimeters of water, is generally recommended, and may be beneficial for all intubated and ventilated patients. A high PEEP may be clinically necessary for patients with restrictive lung diseases, such as ARDS. Avoid to use zero PEEP although it is possible. PEEP is usually constant in all ventilation modes. An exception is in biphasic modes where PEEP alternates automatically between two set levels. From variables to mechanical breaths. So far, we have learned all 5 essential variables. With this knowledge, we are now ready to define mechanical breath types. This task requires just 3 variables: triggering, cycling, controlling. PEEP is applicable for all breath types and targeting is paired with controlling. Here we need to explain 2 terms, mandatory breath and spontaneous breath. If a mechanical breath is time-cycled, it is a mandatory breath, MB. With MB, the ventilator does all or most of work of breathing. MB has 2 types. If a MB is time-triggered, it is a ventilator-triggered mandatory breath or VTMB. It is also known as control breath. If a MB is patient-triggered, it is a patient-triggered mandatory breath or PTMB. It is also known as assist breath. If a mechanical breath is patient-triggered and flow-cycled, it is a spontaneous breath or SB. With SB, the patient does all or most of work of breathing. The SB can be supported or unsupported by the ventilator. Classification of mechanical breath types. Here is a 3x3 matrix for classification of mechanical breath types. One dimension is based on triggering and cycling. Dependent on the selection, a mechanical breath can be either a VTMB, PTMB, or a SB. The other dimension is based on controlling. Dependent on the selection, a mechanical breath can be either a volume, pressure, or adaptive breath. Combining the two dimensions, we get 8 breath types. There is no volume support breath because flow cycling is impossible with volume controlling. However, there is a mode called volume support. Do not mix up the two. These mechanical breath types are critically important because they form the foundation of conventional and adaptive modes. When facing an unknown ventilation mode, if you can identify correctly its essential variables and breath types, you can pretty much tell what it can do and where it can be used, regardless of its given name. In this learning module, we learned 5 essential variables: triggering, cycling, controlling, targeting, and PEEP. The knowledge of essential variables is very useful because the variables are directly related to ventilator control parameters. By applying this knowledge of the essential variables, we identified 8 mechanical breath types. The mechanical breath types are the foundation of ventilation modes. Now we are well prepared to proceed to the next module, ventilation modes ABC.